Hello everyone, welcome to the Cambridge University Astronomical Society's weekly talk. I'm Xavier, the chairperson of the society. So tonight we have Prof Chris Done here with us to talk about black holes, Einstein's gravity, and rocket science. So a bit more about our speaker. After getting her PhD from Cambridge on X-rays from black holes, Prof Chris Done went on to NASA Space Flight Center on the NRC fellowship for 2 years. She returned to the UK on a 2-year junior and then 5 years junior research fellowship from the UK Research Council for getting tenure at the University of Durham in 2000. She was promoted to full professor in 2006, becoming one of the first women to hold this post. She is also a non-secondary visiting professor at the Cabinet Institute for Physics and Mathematics of the University of Tokyo. She spent the academic year 2016-2017 in Tokyo on a sabbatical, working with the Japanese Space Association, a space agency. Notably, Prof Chris is one of the only 2 European scientists supported by the European Space Agency, part of XRISM, the next Japanese-US X-ray telescope. She is the chair for one of the science working groups for this mission, as well as a member of the Science Management Committee, which advises the mission principal investigator. She is also chair for one of the science working groups for the Athena X-ray satellite, due for launch by the European Space Agency in 2030, and has served as the overall chair of the NASA Chandra Time and Mission Committee. The other institutions of SB include being awarded the Royal Astronomical Society George Dowling Lectureship for a distinguished and eloquent speaker in 2019, and being invited on the Stephen Murray Distinguished Speaker Program to cover USA in 2018. Without further ado, Prof Chris, please.
Okay, thank you very much. And it's lovely to see people in person. I'm so excited that this is possible again now. So today we're going to talk about black holes, Einstein's gravity, and rocket science. And in my bio, there was all that stuff about rocket science. So why do we need rockets to go and look at black holes and explore Einstein's gravity? Hopefully by the end of this talk, you'll know. So where are we going? Where? Come on. Yeah. Okay. So the plan of the talk is we're going to have a look at black holes. What are they? How could they form? And how could we ever see them? For those of you old enough to remember a sci-fi series called Red Dwarf, there was a great quote there where it was black holes. Your basic color of black holes, well, they're black. And space, your basic space color is black. So how are we ever going to see them? Looking for a black hole on the black background of space is not a great plan. So what we're going to do is we're going to walk through how we could ever see them. But first, let's start with gravity. Black holes are extreme gravity. And so the first question to ask is, well, what is gravity? And Newton's gravity, the sort of stuff we learned at school, it's great at calculating the effect of gravity. Actually, to send rockets to the moon, you only really need Newton's gravity. It's amazing the synthesis of ideas he made, that maybe the same force that made the apple fall on his head, maybe that was the same force that kept the moon in orbit around the Earth, the same force that kept the Earth in orbit around the sun. An amazing leap of imagination, as well as of understanding how to formulate that in terms of equations. But in terms of the bigger question, what is gravity? Not just how do we calculate gravity, but what is gravity? Newton famously said, "I frame no hypothesis." Actually, he said it in Latin, so it sounded a lot better. But what it means is, sorry, mate, haven't a clue. And that's where it stood for hundreds of years until Einstein came along. And Einstein's gravity gave us not just a better way to calculate the effect of gravity, though it certainly does that, it gave us a way to think about it. It gave us a way to answer that bigger question, what is gravity? And so one of the ways to think about it that people often use is you think of the surface of space like a giant trampoline. If there's nothing on the surface of the trampoline, it's a flat sheet. And if I roll a very, very light ball across it that doesn't really disturb the surface of the trampoline much, it will go in a straight line at a constant speed. But if I now put something very heavy on it, like a bowling ball, then that will curve the surface of the trampoline. And if I roll the ball across, it'll now go in a curved path because the surface on which it's traveling is curved. But there's a bit of an odd thing about that analogy, though, which my dad spotted. He said, well, surely that only works because the trampoline's in the Earth's gravitational field. And I'm going, yeah. A better analogy is the ants. So I'm not a biologist, but I've got some very, very obedient ants. I've got two very, very obedient ants, and I set them off on a flat surface, and I say, head north, head due north. The ants are very obedient, and I've put ink on their paws, claws, whatever ants have. I'm not a biologist. So left foot, right foot, middle foot, left foot, right foot, middle foot, left foot, right foot, middle foot. They're walking in a straight line at a constant speed. And if I set them off on a flat surface and they're parallel, they're going to remain parallel. They're going to be always at the same distance with respect to each other. Now, suppose I set them off from the equator of a sphere and I say, head north, head due north, left foot, right foot, middle foot, left foot, right foot, middle foot. And as they're heading north, the one on the left looks over its shoulder and I'm sure they're getting a bit closer. And the one on the right is looking, going, no, really, they're getting much, much closer to me. Now, they could think that their paths are being drawn together inexorably by some strange action at a distance force, dragging them closer together. Yeah, they could. Or they could just think they're walking on a straight line, in a straight line path, a natural path, on a surface that's curved. And so this is the way to think about gravity, that the Earth orbiting the sun, it's walking in a straight line path, but it's walking on a surface that's curved. It's responding to the curvature of space. And we're good Einstein relativists here, so it's not just space that's curved, but time as well. So it's just responding to the curvature of space and time under its feet. And so it's walking in a straight line path on a surface that's curved. Yeah. So if we're going to make a black hole, we're going to need a lot of gravity. And the most gravity we've got in our solar system is in the sun. So here's a cut through of our solar system. And this yellow blob is representing the sun. Here's the Earth, the green blob, and then the red circle is the Earth's orbit around the sun. And the white lines are representing this curvature of space and time as you get closer to the sun, as the mass of the sun is bending space and time more. Okay, but we want to make gravity stronger because we want to understand black holes. If that's as much mass as we've got, we can't really do very much with it. But if we could squash it down into something smaller, then we could get then into these regions of more highly curved space and time, of stronger gravity. So if we'd made gravity stronger by squashing the sun, what we're saying is we've made a bigger dent in the surface of space and time. And so we'd have to have a lot more energy to get out. So the speed at which we'd have to leave the surface of the sun in order to escape would be higher. Well, let's do that again. Make gravity stronger and stronger. We've squashed the sun further and further down. We can now get at these regions of really highly curved space and time. Now we've really got to run very fast, leaving the surface of the sun to try and get out the top. Yeah, there's a problem because we can't run faster than the speed of light. So if we were able to squeeze the sun down below this size at which you'd have to be running faster than the speed of light in order to escape, well, you can't run faster than the speed of light, so you can't escape ever. And so this defines a point in space and time called the event horizon. This is the event horizon of the black hole. And it's not that there's anything there. Whatever remains has been crushed to an infinitesimal point of infinite density called the singularity at the bottom. At least that's what the equations say. And so there's nothing special here, but it's the point beyond which light can no longer escape. So one way of thinking about this that's actually mathematically correct is to think about space and time itself as falling in towards the black hole. And far away from the black hole, it's falling in, but not very fast. But as you get closer and closer, space and time are falling in faster and faster. And at the event horizon, it's the point at which space and time are being swept in at the speed of light. So if I'm a photon and I'm trying to get out, it's like swimming in a river. If the river's coming past me with some current speed, if my swim speed is faster than the speed of the current, I will make progress. I will go forward, even if not very fast. But if my swim speed is not faster than the current, even though I am swimming forwards, I am going down into the black hole. So this is the way to think about what happens to a beam of light. If it's trying to get out, it's swimming, but space and time are falling in faster than it is, and it gets swept backwards in towards the singularity. Okay, so that's defined as the first kind of special point, this radius at which not even light can escape, this event horizon or Schwarzschild radius. Okay, it's quite small, really. It's 3 kilometers for something the size of our sun. What does that really look like? Well, 3 kilometers across the center of Cambridge. Mass of the sun, that's quite big. But how big is really the mass of the sun? Well, let's think about something smaller scale. Can you turn because this doesn't seem to be working. Okay, let's think about something smaller scale and do it with the Earth. So if I was to take the Earth and compress it down to the size of its event horizon, I'd have to squeeze it and squeeze it and squeeze it and squeeze it. Can I hit go again? Down to the size of less than 1 centimeter. Take the entire Earth, squeeze it down to 1 centimeter, and then it's gone down below its own event horizon. And that gives you just an idea for how extreme gravity would have to be to make a black hole. So, why are we even talking about this? Why are we even talking about making black holes when it's obvious that we can't squeeze the Earth down to that extent? Correct, we can't squeeze the Earth down to that extent. That's not a way to make a black hole, but we can get such extreme compression in the life and death of the most massive stars. And so when we're looking at the most massive stars when they get to the end of their gravitational, when they get to the end of their nuclear fuel burning inside, that's keeping the gas hot, that's pressure pushing out against gravity pulling in. But stars are big, but they're finite. And when they run out of that nuclear fusion fuel, gravity never runs away. And so gravity pulls in and pulls in and pulls in. And for the most massive stars, there is no way out of such extreme compression that it disappears below its own event horizon and forms a black hole. But in the middle of forming a black hole, then as the core collapses, it's as if someone took away the floor. If a core collapses, it was the core that was holding up the outer layers of the star. Core collapses, ooh, no floor. And it's like one of those cartoons when the cartoon character runs off the edge of the cliff and for a moment just stands there and then falls. Well, the outer layers of the star just fall. And they fall smack into the core, bounce, explode in a dramatic supernovae explosion where, whoa, come back. There we go. Where one dying star can outshine an entire galaxy of 100,000 million other stars. So a single dying star for a couple of months can be brighter than 100,000 million other stars that are stably doing this nuclear fusion in their cores. It's that dramatic, it's that extreme an explosion. And for the core, there's nothing that can hold it up anymore, and it collapses under its own gravity into a black hole on the black background of space. It sounded terribly plausible to make a black hole that way. How am I going to test this idea? I've just made a black hole on the black background of space. Bad plan. Okay, well, what about how you could test that? Well, to test it, we need something to look at, which is a bit difficult. So we've made our black holes here from the endpoints of the life of the most massive stars. But you can also make much bigger black holes that grow in the centers of galaxies. And this is the center of our own galaxy. And if you home in on the very center, this beautiful star formation. The great thing about astronomy is it's just so visual. And so let's home in on that central region. And over a time scale of something like 10 to 15 years, they've been tracking the motion of stars close to the center of our galaxy. There's something like 20 stars here that they go every few months and they take an image. And then they go a few months later and they take an image. And these stars, their positions have shifted. This is technically incredible that they are able to do this. And so by mapping out the motions of stars, it's kind of obvious that there's something odd about this motion. I'm going to focus on this one here. I've got to wait for it to come back. Here it comes. Oh, a straight line at a constant speed? No, what happened? It came around, swung around and went back. There's something here, but there's no light. The star on the picture is just to guide your eye. And so by tracking the motions of these stars and just using Newtonian physics, it's kind of quite obvious that there's something there with a mass of 4 million times the mass of our sun. Yet there isn't any light from it. Oh, I think that sort of technically was one of these beautiful, beautiful and very heroic observations and set of observations that really showed the black hole at the center of our galaxy and got them the Nobel Prize. But we also, a few years ago, got this incredibly iconic image of the shadow of a black hole. Here's the image here. And it's been estimated that something like half of the world's population have seen this image. It is that iconic. I just want to, again, to set the scene for just how this is an incredible technological feat to see this. So what they're doing is they're looking at the center of this galaxy here. It's quite a big galaxy, 100,000 million stars, some like the sun, some a bit bigger, some a bit smaller. And it's about the size on the sky of the full moon. So it's quite big. If you home in and take an image of the center, you can already see on the optical image of stars that there's something a bit funny about the center. And when you home in on the center, you can see that, oh, there's something kind of squirting out. This is a jet that's being powered by the material that's falling into the black hole. And then homing in again, what they're seeing here, I mean, it's incredible. There's a shadow, there's a dark bit in the center and a ring of light around it. They're actually seeing this is the shadow of the event horizon of a supermassive black hole in the middle of that galaxy. And this is incredible. So the picture I showed you before of the stellar orbits, the resolution that they required here is 2,000 times smaller than that. It's the equivalent of being able to read the newspaper newsprint from here when the newspaper's in a cafe in New York. Yeah, just think about that. That's what they were able to do here. This is technologically incredible. And yeah, that's amazing. But I want to talk you through some even more amazing things, because to see a shadow, you need a light source. And there's a light source kind of around this black hole. What's happening is there's some quite tenuous gas that's falling into the black hole. And before it goes underneath the black hole event horizon and is lost to the universe forever, some of the immense gravitational energy that it's acquired on its way down, it's emitting in the form of radiation. Very, very dim. It's very, very faint. But it is emitting some small amount of light. And that brings us to think about another of these radii, these special radii. There's the black hole event horizon, where you have to be going radially outwards at the speed of light. But if you weren't going radially outwards, what if you were going tangentially? Turns out there's a point that's 1.5 times further away, where if you're going at the speed of light at this radius, you can orbit round. And so this radius is important because actually that's part of what we're seeing in this ring. We've got this faint emission from the accretion flow as it's falling towards the event horizon. And those light travel paths, they're walking in a straight line on a space-time that is very, very curved. And so their paths get curved dramatically. And it turns out it's easier to see the ones directly behind the black hole because their paths get curved over the top and round the side. And what we're seeing here is this, these paths where the photons are almost orbiting the black hole and coming from behind and coming out to us. And that's what's picking out the shadow of the black hole that we're seeing here. So yes, technologically, an amazing tour de force. And very very dim emission. So surely it would be a lot easier to see if it was brighter. So what about looking at them when they're easier to see, when they're actually accreting a whole load of material, and when that accretion flow isn't just this kind of dim, wispy emission, but is big and bright and booming? Good idea. So what you can get, going back to the stellar remnant black holes that we talked about as being the kind of easy, plausible way to form a black hole. Well, stars actually aren't normally like our sun. Our sun is alone, has no friends. Most stars hang out with their friends. And so if one star runs out of its nuclear fuel, collapses and becomes a black hole, the companion star can be lunch. And so what you can have is you can have a companion star, which is somewhat too close. And then the material on the edge of the star sees more gravity towards the black hole than it sees towards its own core. And so it just falls off into a stream and forms a ring of gas. It's got to form a ring because these two stars are orbiting each other. So it's got angular momentum, so it can't fall straight because it's going off at a tangent. So we form a ring of gas around the black hole. But a ring of gas, it's not like the planets around the sun. Planets around the sun, you have to go faster when you're closer in. So Mercury is going round faster than the Earth, and the Earth is going round faster than Jupiter. But there's no connection between them, so that's fine. But here I've got a ring of gas, and the inner edge of the ring is trying to go around faster than the outer edge of the ring. And so they kind of rub against each other. They're connected together. And so that kind of friction heats up the gas and makes it glow. And there's so much gravitational energy here that it makes it glow not just red hot or even white hot, but it makes it glow X-ray hot. So the signature that you're then looking for these bright, intensely luminous accretion flows is that they should be bright, they should be intensely luminous in X-ray light. So what we want to do is we want to look at the sky with X-ray eyes, because then we'd see nothing. Because if we stand on the surface of the Earth and we look up at the sky in X-rays, our atmosphere is completely opaque to X-ray radiation, which is good for our DNA, but very bad for our understanding. So if we're wanting to look through our atmosphere, obviously we can look through in the visible range, and we can look through in the radio range as well. But the rest of our atmosphere is like a brick. All these other wavelengths of light that are telling us all sorts of information, they get to the top of the Earth's atmosphere and then they're absorbed. And our telescopes on Earth don't get to see them. So that means we get to play with rockets. I told you we'd get to rocket science. And so in the early days of the space race, when people started being able to get X-ray detectors or to get rockets above the surface of the Earth, get them above the atmosphere, one of the early experiments was, why don't we stick an X-ray detector in the nose cone and see what we see? And so they flew an X-ray detector in one of these early rockets. And the things they saw were completely unexpected at the time. The things they saw were things like this. They were seeing intensely bright X-ray sources that were marking out these bright accretion flows. And so in many ways, it was rocket science, X-ray astronomy in rockets that transformed the study of black holes from being some speculative extrapolation of Einstein's gravity to real observable science, and also got the Nobel Prize for Giacconi in 2002, because actually this was the first evidence that the black holes really existed, that they were real astrophysical things you could observe and not just some wildly speculative extrapolation of Einstein's gravity. So now let's look at the sky with X-ray eyes. But first, let's look at the sky with optical eyes and orient ourselves on what we're going to see. So often when people show you the entire sky, you've got to put something that's three-dimensional onto a two-dimensional picture. So generally, you line it up. This is the center of our galaxy. And then this is the plane of our galaxy, the Milky Way. So you take 100,000 million stars like the sun, some a bit bigger, some a bit smaller, tie them together by their own gravity into this big disk of stars that's much narrower than it is when you look at it face on. So the plane of our galaxy is here, the center of our galaxy is here, and then looking up and down gets you out of the plane of the stars of our galaxy quite quickly. Okay, that's what we see in optical light. What do we see now when we get above the atmosphere and look in X-rays? There we go. And there's some sources picked out in red here that very obviously follow the distribution of stars in our galaxy. You can see quite clearly, here's the plane of our galaxy. You can even see that this is the kind of bulge towards the center of our galaxy. So there's a population of X-ray sources that follow the population of stars in our galaxy. And these are the ones like we just described, where you have one star that's collapsed into a black hole and a companion star that's a source of material feeding that X-ray bright accretion disk. That's kind of like an X-ray halo around the event horizon of the black hole. The black hole itself is very black, but the material falling in from the companion star, which is energized by that incredible gravitational potential that it's falling down through, that's highlighting the position of the black hole that we can't see. It's like a neon sign. It's an X-ray sign going, hey, look at me. So that's the red sources. A lot of those are like this. But you can also see there's a lot of blue faint sources scattered around seemingly randomly across the sky. What are they? Well, they're some of these supermassive black holes that we talked about earlier. Centers of most galaxies have a supermassive black hole. The center of our galaxy had a supermassive black hole, but we couldn't see it because there's basically almost no material falling into it at the moment. The center of the M87 galaxy with that iconic shadow of a black hole, very, very dim amount of accretion giving us the light by which they could see that shadow. But some supermassive black holes have a whole ton of material falling onto them, and then they are dead easy to spot because, again, we get these X-ray bright disks, which are highlighting the position of the black hole at the centers of these galaxies. So I'm just going to talk you through what we can do with that X-ray emission. How can we use that X-ray emission to sneak up on some of this incredibly strong gravity? So what we're going to do is we're going to think a little bit more about what we might expect to see from this material sliding down towards the black hole event horizon. So if we were looking at the surface of the sun, I could take its spectrum. And the sun is pretty much a single temperature thing. And if I plot its spectrum, the amount of intensity I get as a function of wavelength or frequency of light, it's a very clear peaking in the yellow part of the spectrum, and that's called a black body. And all it cares about is, it doesn't care what this stuff is made of, it just cares how much luminosity you want to dissipate across whatever area you've got, and that completely determines this peak temperature that we see. Okay, so how can we use this to understand what we might expect from this black hole accretion disk? So let's just think about it. Well, we know something about gravity. Gravity is that curved space-time. And as we get closer to the black hole, the space-time gets more and more curved. So we get more and more of this gravitational energy out. So far from the black hole, we don't have very much curvature. We don't have very much gravitational energy. We've got a lot of area over our disk to kind of dissipate this. So it's going to be very low temperature. But as we go in, we get more energy out, and we're dissipating it over a smaller and smaller area. And so it's kind of easy to see that what we expect is that this X-ray hot disk is going to be a sum of all of these temperatures that are getting hotter and hotter and brighter as we get towards the event horizon of the black hole. So we're going to have this emission peaking really close to the event horizon of the black hole. It's going to be an intense light source, really in that curved space-time region. And that's going to keep on giving us more and more luminosity at higher and higher temperature until we get to this innermost radius. What sets the innermost radius of this disk? Well, obviously, it's got to end before the event horizon. And actually, it must end before that light orbit, because you can't have material going around at more than the speed of light. But actually, Einstein's gravity is more subtle, definitely more subtle. And the disk doesn't actually extend down to these radii that we talked about before. It stops about a factor 2 earlier than that, because Einstein's gravity is just a little bit different. I'm going to talk you through this because actually it's easy to explain. If I'm talking about orbits, Newtonian gravity, it gets stronger as you go towards, towards the object. So Newtonian gravity is telling us we'd like to get closer in. But things that are orbiting, they've got angular momentum. And if you try and go closer in, then like a skater, pull your arms in, you try and orbit closer, you'll end up going around faster. And if you go around faster, if you try this on a kiddie's roundabout, there's a force that pushes you the other way. So orbits are kind of a balance between gravity trying to pull you in, but if you're orbiting around, that kind of pushes you out. And there's a minimum point here where everything's nicely balanced, and that's a circular orbit. If I drift outwards, gravity tries to pull me back in. If I come further, if I drift inwards, then I start trying to go round faster, at which point I get thrown out. So these things are stable. If you look at the shape of this curve, I'm sitting at the minimum. That's a stable orbit. Okay, now let's see what changes when we go to Einstein's gravity. Well, kind of not much really at first sight. There's an extra term that adds to gravity, makes gravity stronger, but only on really small scales. You don't notice it normally, but as you get to smaller and smaller scales, there's something that starts to dominate. And so this nice stable curve that we had, if we get too close, turns over. But how close is too close? Let's go do it. There's our nice stable curve. If I drift inwards, I start going around faster, which pushes me out. If I go out, gravity pulls me in. But if I start getting a bit closer to the black hole, that friendly crash barrier, it's getting smaller and smaller, and now has disappeared. And now at this point, if I drift outwards, gravity will pull me in. But if I drift inwards, I've lost my crash barrier and I'm just going to spiral straight down. So this is called the last stable circular orbit. And it's at a factor of 3 larger radius than the event horizon. Okay, so we're not going around at the speed of light. We're only going around at something like 30% of the speed of light. It's not the event horizon, but it's the place where gravity just gets a bit funky. I can happily orbit round in here. I can go in a circular orbit. The only problem is I need to be like a fly-by-wire plane. Fly-by-wire planes, they're unstable, but any kind of small kind of imbalance, the computer control automatically kind of pushes it back. You know, most particles in an accretion disk don't have a computer controlled rocket to push them back. So most particles in an accretion disk, they get to this last stable circular orbit and it does what it says on the tin. It's the last stable circular orbit. And from then on in, the particles spiral into the black hole. This sets the inner edge of the accretion disk, according to Einstein. But does it according to the universe when we go and look with X-ray eyes? Okay, let's go and look with X-ray eyes. Do we see spectra that look like this? The answer is yes. There is real data here, real X-ray data in red points and in the green points. And then this red dash line shows you basically this kind of spectrum, this kind of getting hotter and brighter as you go inwards on a disk. So the data is here and the model is here. That's really quite impressive. Okay, there's a little bit of a tail to higher energies, but the main amount of power is coming out in something really like what that back of the envelope Einstein's gravity predicts. But is it really the last stable circular orbit? How could we tell? I mean, just from one snapshot, it's a bit difficult to know quite what this radius is that it's telling us. And is it really constant? That's the key prediction of Einstein's gravity, that this is something set by the nature of space and time and gravity, and it won't care how much mass accretion is coming in through the disk. So if it's constant and the mass accretion rate changes, then we know how the amount of gravitational power is going to change as we change the mass accretion rate. And if it's just like this thermal emission, we know how the temperature should change. So we can go and watch the luminosity of these black holes change. This is 2 years in time, and this is the X-ray luminosity, and they do amazing changes in these sorts of days and weeks and months timescales. And if we now take some of those spectra and look at them and measure the amount of luminosity and measure this peak temperature, there's a selection of 6 of them here, but I have many, many more. And for each one, I've got a measure of the luminosity and a measure of the peak temperature. So each one of those is 1 point here, a measure of the luminosity and a peak temperature. Then the next one can get a measure of the luminosity here and the peak temperature, and here, and here, and here, and here. And then I plot those all together. And this line shows what would happen if that innermost stable circular orbit, that innermost orbit of the disk stayed constant, like Einstein says it should. That's a pretty good description of those data. There is a fixed size scale in here. I can even do it in terms of radius. There is a constant size scale in here that despite the large change in luminosity, despite the large change in mass accretion rate through that disk, the size scale picked out as the inner edge stays constant, just like Einstein said. This is pretty much strong gravity. There is, this is almost the strongest gravity you could hope to observe. And it's absolutely generic. We know of a lot of these accreting black holes in our galaxy. Here's a selection of 6 of them. And here they all are with this characteristic luminosity going as the 4th power of temperature that tells you there's a fixed innermost size scale to this disk emission. They all do it. But it gets us to something else as well, because the thing we really want to know about, the key thing about Einstein's gravity is it predicts there's an event horizon. So this material gets to the innermost stable circular orbit and spirals down and is lost to the universe forever, according to Einstein. According to Einstein, all that energy, all that orbital kinetic energy it's got, where did that go? Well, it went down into the black hole, past the event horizon, and never came out again. And that's more or less what we're seeing here. We see this strong disk emission. There's a little bit of high energy tail because there's a little bit of energy that escapes from the top of the disk without thermalizing, but this material carried twice this amount of energy as kinetic energy. Where'd it go? Well, down the black hole. That's where it went. And nature's been really kind to us because it's given us a comparison set. The stars that aren't quite massive enough to collapse to a black hole, there's a last stable state of matter called neutron stars that they can just about get caught up on. But the size of a neutron star is basically the size of its last stable circular orbit. So it's honestly like we take the black holes and at the last stable circular orbit, we put a surface. And so all of that kinetic energy, all of the orbital energy that the material has that in the black hole goes smoothly down into the black hole, well, for a neutron star, it smacks. There's a complete recovery of all that energy. It smacks onto the surface and radiates. And we see it. We see it very easily. This is data. You can see, whoops, missed. You can see there's roughly as much energy coming out again in this smack layer as there is in the rest of the disk itself. And while absence of evidence isn't the same as evidence of absence, that's pretty consistent with there being a real event horizon in the things that we're calling black holes. So this is just illustrating how we can use the X-rays we get from rocket science to explore Einstein's gravity in the strong field regime. But of course, one of the, slightly surprised to see that one. Did I go backwards? Yes. But But one of the extreme strong gravity events, the most extreme strong gravity you could ever hope to measure, is if you take two black holes and merge them. And so here you've got play that movie again. If you go from the sorts of stars we were talking about, where you've got a companion star and a black hole, well, if the companion star itself is massive enough, maybe it can also collapse to a black hole. And then you'd have two black holes on the black background of space going around each other. And because they're going around each other, that dent in the surface of space and time is moving. And so as they spiral around each other, they're actually sending out a wave of gravitational bending of space and time. And that means that they're losing energy, and that means they're spiraling closer together until those two black holes themselves are on the innermost stable circular orbit, at which point the two black holes themselves spiral in together and their event horizons merge, giving you the strongest burst of gravitational waves. And it's that was discovered about 5 years ago now in the first detection of gravitational waves, the signature of two event horizons merging. And the top gives you the signal that they saw. The middle panel shows you what was predicted in advance that this merging of event horizons should look like. And again, technologically incredible to be able to detect such signals. And yet they were able to do it. Oh, another Nobel Prize here. And so we're out of time. So I'm going to wrap up here. Black holes, they are the ultimate extrapolation of Einstein's gravity. But an isolated black hole on the black background of space, nah, that's really not a great way to find them and explore gravity in these intense strong gravity regimes. But what we've seen is there's evidence from the center of our own galaxy, looking at the orbits of stars in that strongly curved space-time close to the supermassive black hole at the center of our galaxy. In M87, we saw that iconic image where a very tenuous accretion flow produces just enough light to show the shadow of the black hole. But the life got so much easier when the accretion flow was much stronger and it was lighting up the positions of the black holes with this incredibly bright X-ray hot halo of gas. And because these higher accretion rates just made them so much easier to see and pinpoint and detect. But it required us to get above our own atmosphere to get rockets with X-ray detectors above our atmosphere to be able to see this. And that using X-ray astronomy, we've been able to explore Einstein's gravity, explore some of the consequences, explore things like predictions like there's a last stable circular orbit, explore it, whether or not there's an event horizon. But some of the most dramatic tests of Einstein's gravity in the strong field limit have come from the very recent detection of gravitational waves, where you have merging black hole event horizons. And everything so far is telling us that Einstein's gravity is the right way to describe gravity, which is fabulous news for a relativist like me. But at some point, we have to have something better than Einstein's gravity. We know Einstein's gravity doesn't fit in very well with the rest of physics that we describe in terms of particles and fields. We know that it doesn't play well with quantum mechanics. We've got two fabulous bits of physics. We've got Einstein's gravity, we've got quantum mechanics, and they won't talk to each other. At some point, we need a better theory of gravity. At some point, we need some sort of quantum theory of gravity. And yet, what this is telling us is it's telling us that getting observational evidence for that better theory is going to be very hard. Thank you. Okay, questions? Oh, sorry, are you gonna go for it?
Thank you, Prof Chris, for the amazingly animated talk. Now we have about 15 minutes for questions. So if you would like to ask a question, you can raise your hand and ask mine. We can also take a few questions from our online audience. So if anyone watching over the Zoom has a question, you can put it in the chat.
Well, I can always repeat the question, and then it will go on Zoom. So.
Right. First question, try to
Great question. I know it took them a while to show that. So the question was, okay, the first X-ray detections, how did they know it was one of these black holes accreting material from a companion star? Did it take them a long time to figure that one out? Well, yeah, it did actually. So I talked also about neutron stars, how you could have neutron stars that were quite similar in many ways. They're quite extreme. It's just they're not quite extreme to have disappeared under their own event horizon. They're only about a factor of 3 larger than their own event horizon. So they're quite extreme objects. And it still can sometimes be a little bit difficult to tell whether you're looking at a black hole or a neutron star that's being highlighted by one of these intense gravitationally powered disks. But what they did for those first X-ray sources was they found the optical counterpart, because optical telescopes, we have a lot more expertise. We've been working with optical telescopes for a lot longer. And then managed to get the companion star and its orbit. They could track its orbit. And using that, they could weigh the mass of the companion that it was orbiting around. And the ideas of what can hold up against gravity, there's this neutron star that's almost as extreme as a black hole. But once you get past 3 times the mass of our sun, everyone goes, nah, no way. So when you've got one of these orbits, and you can weigh the mass of the black hole by following the orbit of the companion star. If it's more than 3 or 4 times the mass of our sun, it's like, yeah, game over. It's a black hole. And that's how they were able to really show that the first discoveries of sources like this, they could really show, okay, some of these are definitely more than 3 or 4 solar masses. Neutron stars aren't going to make it at this stage, and so it has to be a black hole. But it did take them some time. More questions?
Right, we will have one from the online audience. So one can ask, presumably when the frequency is bright enough X-rays, it's also bright in visible light. Can we do optical astronomy on that?
So I'll just read that question out in case you didn't hear it. So the idea is, okay, these accretion disks, they're bright in X-rays, but surely they should also be bright in optical. So can we look at the optical emission and study black holes from this optical accretion disk emission? And the answer is yes, we can indeed. Can we go back to that picture of let's go back to that one, that'll be good. So what you can see here is the outer edges of the disk, they're quite low temperature compared to the inner. And so the outer edges of the disk, they can emit in optical, but they're not as bright as the inner X-ray region. And so they're not so bright, but yes, we can see them and we can study them. The problem is, as well as not being so bright, they're not close to the event horizon. And the things we really want to explore are the really strong gravity down in here. So yes, we can study these from the emission over here on the outer regions in the optical from Earth. But the bits we really want to play with, the strong gravity or the funky stuff of Einstein's strong gravity, that comes out much closer in. And so the X-rays are really the only place to go for that. Yes, there is a good reason why it's so asymmetrical. So if we go back to that iconic image of M87, and one of the things you notice about this iconic image is it's kind of lopsided. There's more emission one side than there is on the other. And if we go back to the pretty picture with all the light rays on it, tries this one, right? Okay, so what you've got, the material in the accretion flow, it's actually trying to orbit. It's not falling straight down. It is trying to circle around, a bit like those accretion disks, but it's got a larger scale height. So it's going sideways and trying to orbit the black hole as well. And so one of the sides is coming towards us, and one of the sides is going away. And because this stuff is moving really quite quickly, then it gets Doppler shifted. The side coming towards you gets boosted in intensity, and the side going away from you is dimmer. And so that's what's giving this kind of lopsidedness to the image. It's actually showing that the material in the accretion flow isn't static. It's trying to orbit around. And so it's moving. And so then the stuff coming towards you is brighter. The stuff going away is fainter. There was another question somewhere. Yeah. Mm-hmm. So it's not going through the black hole, it's going around it. So that's the, we were talking about photon orbits. So if this is my black hole, if I'm here and going that way originally, the gravity is going to bend me round. And so if I'm over here, I can't see a piece of light that's trying to get through the black hole, but I can see the light that went off in this direction originally and went in a straight line on surface that was very curved. And then it can swing round and I can see it the other side of the black hole. Okay, is it possible that black holes could be creating other universes? And this gets us back to the point that I was making at the end, which was, okay, there's this singularity here at the bottom of a black hole. According to Einstein's gravity, according to the best theory of strong gravity we've got, nothing can hold up the collapse to nothing. It just goes to this infinitesimal point of infinite density. called a singularity. And so maybe that itself could spawn off multiverses, different universes, other universes, whatever. How? But wherever you see an infinity come out of equations in physics, that normally means you took them somewhere they didn't want to go. And so when we deal with things that are very, very small, we know that the theory we want to use is quantum mechanics. Quantum mechanics is the theory of the very, very small. And it tells us that very, very small particles don't behave like billiard balls. They behave like waves that are kind of trying to be billiard balls sometimes and waves other times. It's called wave-particle duality. And it basically means we haven't got a clue what they're actually trying to do. But we can calculate it very accurately. Just we don't have a good way of thinking about it. And so when we get to these very, very small size scales of a singularity, we want to reach for quantum mechanics. But we can't reach for quantum mechanics because we're in extremely strong gravity. And extremely strong gravity means you want to reach for Einstein's gravity. But it's on very, very small size scales. So we should really be talking about quantum mechanics, but the two of them won't talk to each other. So our current physics has a problem when we're trying to describe the structure of the singularity. If you talk to any kind of reasonable physicist and say, yeah, what do you reckon to a singularity? They're going to go, nah, it'll have some sort of quantum structure to it. But we can't calculate what that is because we don't have a theory we can take into this extreme sort of circumstance where we're dealing with very, very strong gravity on very, very small size scales. So then you think, well, you know, do we really want to? I mean, it's decently hidden below the event horizon of a black hole, so we're never going to be able to test it. But the other place you want to do this is the Big Bang. It's the beginning of the universe, where you've got very, very strong gravity on very, very small size scales. And until we have a theory of gravity that will deal with these two extremes together, we're not going to be able to explore the fundamental structure of the Big Bang. We're not going to be able to explore the fundamental structure of whatever's at the bottom of a black hole and whether it might be spawning a whole load of other universes as well. Bad question. Okay, so Hawking radiation. What's going on there? The idea is that you get into stuff about space and time and quantum mechanics that's wondrously mind-bending. So empty space isn't empty. By this time, you should just be looking at me going, what is she on? Empty space. In quantum mechanics, you can borrow from the universe. You can borrow energy from the universe as long as you pay it back really quickly. The more energy you borrow, the faster you have to pay it back. So I can borrow energy from the universe and make a particle-antiparticle pair in what was empty space, as long as they quickly annihilate. Okay, fine. Now let's do that just outside the event horizon of a black hole. I make my particle-antiparticle pair, but it's now in an intensely strong gravitational field. And so it can gain enough energy from the gravitational field that I can have one particle actually exist and the other particle get swept down, take my energy debt below the event horizon. So I didn't actually get anything from below the event horizon, but I borrowed some energy from the universe, paid back my debt by borrowing from the black hole, and then put the bad debt down the black hole. And that's Hawking radiation. Yes. So yes, I did not get anything from within the black hole itself. However, I did tap its gravity, and it will, over a time scale that is immensely longer than the age of the universe, evaporate my black hole away? If we understood what singularities were doing. Oh, sorry, I should repeat the question. So the question was, after the evaporation of the black hole, would there be a bare singularity? Was that the question? The answer, according to Hawking radiation, is when you evaporate the black hole, you have evaporated all its mass energy. So it doesn't have a singularity anymore because it has no more mass. So on the Hawking radiation way of thinking about it, you do literally evaporate the entire black hole, which is the singularity, because all of the mass energy, you borrowed it, put the bad debt down the black hole, and eventually that took the entire mass energy of the black hole. Yeah, information. So the information, I got filmed by the BBC. They've done a new The Universe series. And the BBC version, they used Brian Cox. But the version that they syndicate to other countries is they have a variety of presenters, because other countries aren't as impressed with Brian Cox as we are. But anyway, one of their other presenters was me. And so they took me in lockdown to a hotel in Wales in an abandoned quarry in a post-industrial landscape. And eventually we got to talking about the information paradox, and they had me burn a piece of paper on a windswept quarry in Wales. Have you ever tried to burn a piece of paper and do that when there's a wind? Yeah, so after I think 6 or 7 tries, we finally got this paper to go. And I was so keen that it shouldn't actually go out again. I'm holding it and it's burning my fingers. I think I managed to do the proper kind of smile at the camera while going, ah! And but the point was, they were trying to do the information paradox, that like you could burn a piece of paper, but maybe you could sweep up all the photons and work out what had been written on the piece of paper. And I'm going, no, entropy, that doesn't work. And yes, I understand that quantum information, unitary, is different to the sort of stuff you talk about in entropy. It's one of these things that you really have to be one of the aficionados. And, you know, I'm kind of halfway between an observer and a theoretician. I'm really quite happy that if you stuff stuff down a black hole, then you're not going to get it out again in the same way, shape or form. Unitary operator of quantum mechanics or no unitary operator in quantum mechanics, I think my black hole will crush information out of existence. And whether or not that's true, we need a better theory of gravity in order to show me that I'm wrong. Okay, in which case, back to Celia.
All right, that's all the time we have tonight. Thank you everyone for coming, and I hope you enjoyed the talk and learned something. And thank you once again to Prof Chris for the very entertaining talk.
Thank you.
Before everyone leaves, I would just like to remind you that our membership officer Ting is outside the door. So if you would like to purchase your membership to come to more talks or observations, you can do that right here. And otherwise, that's all we have tonight. Thank you so much for coming, and hope to see you guys again.